Hello, everybody, and welcome to WOW 11 for another session. So thank you all so much for your patience during our technical difficulties. We really appreciate you waiting. We have a great presentation in store for you today. We've got Alaa Omar here with us, and he's going to talk about how to build a risk-based failure management strategy. So that being said, if anybody has any questions throughout the webinar, go ahead and drop them in the Q&A panel on your webinar screen. That being said, if we do happen to have any technical issues throughout the webinar, I'll let you guys know and we'll stay in regular contact with you. And if we do need to wind up rescheduling due to any connection issues, we will do that. But for now, we seem to be good to go. So that being said, Alaa, I'm going to go ahead and we'll put your PowerPoint up on the screen here. You should be good to get started. Are you there with me?
Hello, everyone.
All right. Hi, Alaa. You're good to get started.
Yeah. Start?
Yes.
Good. Hello, everyone. It's my pleasure to be with you today discussing one very important subject in our reliability journey, how to build a risk-based failure management strategy. We are going to discuss the failure investigation and the maintenance evolution and how can failure problem be solved, different technique. Then by the end, how to build a risk-based failure management strategy. The big idea is to have a trouble-free operation. Someone can't imagine that one day I can have no trouble, I can have no failure in my critical equipment. But this can be happen. This is a reality. It's already occurred in many field of industry. The problem is how to improve reliability by first working on the right problem, using the right approach with the right technique and the right tools. So we are going to discuss these four rights today, inshallah. Failure. From the very old, failures are considered the enemy of any engineer, technician working in the industry field. When the failure occurred, it appeared as a failure mode. It's observed as a failure mode. So the failure mode is the indicator, all the observation that we get to know that we have something wrong in our assets, in our equipment. This failure is due to an immediate cause, a direct cause that lead to this failure. If we go too much deeper in our investigation, this immediate cause is due to some contributing causes. Some other deeper factor lead to this immediate cause, which lead to this failure to occur and be observed with this failure mode. With the root cause analysis, we go too much deeper in order to reach the roots of these causes that lead to these contributing causes or consequences led to the immediate cause going to the failure. If you keep the failure and do nothing, it can reach the worst level of the failure, the breakdown state, the total performance loss. If there is a protection system available, it will trip your machine to protect your devices. If there is no protection, it can go to damage or something like that. So it's a breakdown, the worst level of the failure. If you go earlier, in order not to reach this very worst, very bad state of failure, it's just a functional failure. Maybe the equipment still working, machine still running, but it didn't give the required function satisfactory. So it has a functional failure. The function is lost. Machine is still running, but the function is lost. So it's a functional failure in this state. If we go too much earlier, it is just a potential failure, an early sign of failure. We are going to discuss these three levels soon. This failure propagates through a mechanism, through a process. It propagates with this process. This is the failure mechanism till it reaches the failure state, till the equipment be unable to perform the required function. When the failure occurred, it has an effect. The failure effect is the consequence occurred after the failure in our production facilities, in our equipment, in environmental impact, whatever. There is a failure effect. The consequence occurred after the failure. This effect sometimes is risky, sometimes is moderate in its risk. So there is a failure risk coming from the failure effect. Actually, to investigate any failure, we need to know all these items related to this failure, which is sometimes or in many times it will not practical to get all this information. We need a lot of time, a lot of effort, a lot of manpower working on the failure analysis. But to make a real investigation for the failure, we need to get all this information about the failure. So what to do? Let's see. How we manage our failure from the very old, how we manage our failure. In the beginning, it's just corrective maintenance. Corrective maintenance means we keep our equipment and our machinery and our asset working until they fail. We do nothing. So in this case, the failure reach its worst level, reach the breakdown state, the total performance loss, the zero performance level. So the time needed for the repair will be long, the downtime will be long, process loss will be high. As well, there is a consequence of failure. The failure start, propagate. When reaching this breakdown state, there is maybe some other failure occurred due to the main failure, some other effect, some other component badly affected due to the failure. So the spare part consumed as well, which is a cost, will be too much high. For that, we used another strategy to prevent this bad situation, to prevent failure from occurring from the first time. Preventive maintenance. From the name, we need to prevent. Prevent what? Prevent this failure. So we used a time-based strategy to put regular activities in order to prevent the failure from occur. So we do our best in order not to go after the functional failure, not to reach this breakdown failure. The maintenance strategy upgraded more and more, going to the predictive maintenance, the condition-based strategy, using the tools and technology in order not to deal with the functional failure, but to catch its very early sign of failure, using the vibration analysis, thermography, ultrasound, and so on, using all these different tools and techniques in order to catch the early sign of failure, the potential failure. Then finally, we go to the proactive maintenance. Proactive maintenance is a risk-based strategy. With the proactive maintenance, we found that we do a lot of effort to prevent the failure. We do a lot of measurements in order to catch the early sign of failures. So, based on, we spend a lot of money to prevent failure. But have the same impact failure qualifiers according to the severity of the consequence. Not all the failures have the same effect. Not all the failures are risky. We have catastrophic failure, critical, major, minor, and marginal. So it's not logic to spend a lot of money to prevent a marginal failure or a minor failure. It's not logic to go with the condition monitoring and use the technology and the tools and the certified technicians to get the data to prevent or to catch early sign of a very minor marginal failure. So we need to think on the catastrophic failure, where to put our resource. We need to make optimization for our maintenance activities. So within the proactive strategy, we need to make this optimization. So we have the reliability center maintenance tool, FEMIA tools, and so on. For the equipment failure now, it should be defined, the failure, it should be defined the functional failure. It's not more the breakdown. Breakdown is the worst case of failure. And potential failure actually is not a failure, it's just early sign of failure. So the failure today is the functional failure. And we need to take action, especially for critical equipment, to catch it earlier. But what if the failure occurs? What if the function is lost? We need now to investigate the failure. To investigate the failure, we need to know its failure mode, its indicator, its observation. We need to know its failure mechanism. We need to check its effect and the risk of its effect in order to how to proceed investigating the failure. The factors that influence equipment failure can be categorized under these different factors. Design error. Maybe there is something wrong with the design. It is not suitable to the application. So equipment fail. Maybe there is some changes occurred in the operation parameters. Let the equipment be not suitable. So you are operating it outside its design operating envelope. So it failed. As well, the failure may be due to faulty material. The material is not suitable for the condition of operation, for the application. Maybe improper fabrication and construction. And this includes the installation, commissioning, connecting with other equipment, and so on. Maybe improper operation. Operator don't follow the standard operating procedure. Operator make shortcut. Operator overload the machine. This can lead to failure. Or inadequate maintenance. Not executing the maintenance program or executed it with wrong intervals. Or maintenance error. Not doing the maintenance with the standard maintenance procedure. Don't using the right tools to execute the maintenance. All these reasons can lead to failure. Now, if we stop for 1 minute and think about these reasons and our maintenance program that we put, including the preventive, the predictive activities, many of these factors can be solved with the maintenance program. The maintenance doesn't influence many of these factors. What the maintenance task will do for one operator overload the machine. What the maintenance task will do for improper or inadequate maintenance program. What the maintenance task will do for design error. or installation problem. Nothing. The maintenance is merely one of the many approaches to improving equipment reliability and hence the system reliability. What we need now, we need to have another failure investigation system parallel to our maintenance program to investigate the failure, to get its cause, and what we are doing now in reality in the industry. If I ask these questions, someone will say, yeah, we are going to make troubleshooting. When there is any failure, we will go through the troubleshooting process. Others, we are doing root cause analysis. Others, we are doing a defect elimination. Others, a lot of different approach are available to investigate failures. Which approach to use? Which approach to use to investigate our failures? It seems that the road is complicated. A lot of different approach. So what we need, let's to discuss the main failure investigation approach briefly one by one to know which approach we need to use. From the very old, we are using troubleshooting to solve our failure. It's a very known as it's very old for everyone in the industry. What's troubleshooting? Troubleshooting is a form of problem solving often applied to repair failed product or process. So it's a problem solving technique for our failure, for our incident, for our troubles in the industry. Troubleshooting is the identification of or diagnosis of trouble or failure or incident in the management flow of a corporation or a system caused by a failure of some kind. The problem is initially described, appeared as a symptoms of malfunction, this failure mode. The troubleshooting process look for these symptoms and investigate it to get the causes that lead to these symptoms in order to put the corrective action for the causes, not for the symptoms. So troubleshooting can be defined as a logical, systematic search for the source, for the cause of a problem or failure. So it can be solved. And the product or process can made operational again. But there is one misconception. When you open any manual, any OEM manual, you will find one chapter about the troubleshooting. So the very easiest way when we have a problem is to go directly for this manual, open the troubleshooting chapter. You will find one very fine table or flow chart, put the failure, the possible causes, and the remedy of every cause. Looking for known errors in a database or library is not troubleshooting. We can call it instant matching, but in reality, it is not troubleshooting. This can be useful tools for problem solving. Actually, sometimes we did that. When you have a problem with your one software in your laptop, you can restart your laptop. It will work well. What we did, we look for the troubleshooting, restart. We restart. Failure, repaired. But what is the failure itself? What is the cause of this failure? Actually, we don't know. So we can say that making some trial by looking for any reference about the failure or the manual about the failure to solve it is a troubleshooting. Real troubleshooting requires us to think independently, not just follow instruction, to think in case by case by looking for the failure mode, for the symptoms appeared, looking for our system, looking for this system, think about what occurred, what may be the problem, then try to solve it. But follow instruction is not a troubleshooting. Working through a set of possible fixes without trying to understand the problem is not real troubleshooting. Real troubleshooting requires us to think in a methodical way and choose the best action based on the information, the data that we get and investigate. So the troubleshooting process can be like this flowchart. Firstly, identifying the problem by putting a problem statement, the failure mode, indicating the real failure mode, the real indicator that we have, the observation that we see. Then think about our system. Think we have now one function lost. So we need to think about our system, which component has a problem, to find the faulty component. Then to correct this problem, replace this part, adjust it, whatever is the action, but to correct the problem, then to verify the correction, to be sure that it's actually corrected. Finally, to think how to prevent recurrence of this problem. Is there any task need to be done? We have already our maintenance program to prevent failures. Is this failure, we take care about it in our maintenance program or not? If we have a task to prevent this failure, so why it occur? Maybe the frequency of our task is wrong. Maybe the procedure or the tools we use is not suitable, is not the best. So we need to think how to prevent the occurrence by the end. So find the faulty component. This is where we spend the most of our time thinking about where the problem. If we get it, it will be very easy to correct the problem, to fix it directly. So we can say now that the troubleshooting based on this flow chart of troubleshooting process is to find the faulty component so that it can be repaired and the product or process can made operational again. Troubleshooting is finding the faulty component so that it can be repaired and the product or process can be made operational again. Good. Another technique, so now we discussed two different technique for the failure investigation: instant matching and troubleshooting. Instant matching is just follow instructions without any thinking. Check this one, check this one, check this one till the problem is solved. This is an instant matching. It can work sometimes. And troubleshooting, no, think about the problem, put the possible causes, find the faulty component, take action for this faulty component, then verify your correction. Another technique for the failure investigation may be a little bit modern than the troubleshooting, the root cause analysis or the root cause failure analysis. Root cause analysis is an analysis used to determine the underlying cause or causes of a failure, the unseen causes that lead to this failure. in order to put the corrective action for these root causes to avoid future occurrence of the failure. In many cases in our consultation and training, when I ask people working in the maintenance how you deal with your failures, they said, we are so modern, we are going to use the root cause analysis. So what you are doing, actually, they do troubleshooting. They didn't do root cause analysis. Root cause analysis is something else. Root cause analysis is not troubleshooting. So what is the difference? To be clear, troubleshooting search for the immediate cause that lead to the failure. Where the faulty component, this bearing failed, replace the bearing. But troubleshooting, root cause analysis, think more deeply, more deeply. Go, why this bearing failed? Why it failed? What are the deeper reason or reasons lead to this immediate cause? And go too much deeper till reaching a level that we can say it's the root cause. So what is the root cause? The root cause is the origin source of the problem. By its characteristic, it's hidden. Need deep investigation in order to get it. And you are able to solve, you are able to put a corrective action for it. And this corrective action will prevent recurrence of this failure. The root cause analysis is an analytical technique, analytical methodology that let you reach this root cause. So we use the root cause analysis as a methodology to get to the real origin source of our problems. So the purpose of the root cause analysis methodology is to define an overall process used for defect elimination through the tracking of plant problems, bad actor identification, problem root cause analysis, and resolving as well tracking of proposed solution effectiveness. The root actually usually has three levels. The technical root cause or the physical root cause that lead to some consequence causes which lead to the immediate cause that lead to the problem. And deeper than the technical or the physical root cause, there is a human root cause that lead to the physical root cause, the human factor. And under the human root cause, there is the latent root cause, the deficiencies in organizational systems that lead to human error, that lead to the physical root cause. So we have three levels of the roots. The purpose of the RCA investigation to get to the three levels of the root cause. The most success when you solve the latent root cause. The highest return of investment in this investigation when you put corrective action for the latent root causes. The RCA as a methodology has several stages. As we said, it's not troubleshooting. So it's analytical methodology with a process that start with identification of the failure and putting a problem statement for this failure, looking for the all the information related to this failure and checking its significance, its risk, the risk of its effect. If the failure is not risky, so no need to go through the RCA. Troubleshooting will be enough. After the initiation stage, we go to the second stage of data gathering by collecting a lot of data related to the design, the operation, the maintenance, the event of the failure itself, by making interviews with all concerned in the failure, even if there is contractors, getting all the related information from the operating manual, reviewing all the maintenance record, the history. A lot of data need to be gathered in order to go to the analytical stage using the analytical techniques like fault tree analysis, cause mapping, and so on, to know why this failure occurred. So we need to have a lot of data to make the investigation. With these analytical tools, we will reach the roots. After reaching the roots and know the roots of our failure, we move to the next stage of corrective action. We need to think about and make a brainstorming to put what are the possible solutions. Then to look for the cost benefit analysis. Which solution is the most effective and the most efficient one as well? Then putting the action plan, get the approval, putting the action plan, make the reporting, implement the corrective action, check the feedback after implementation. So it's a very long process that need many resources. It will consume time and consume resource. It's not like the troubleshooting. Troubleshooting is a quick investigation technique, but the root cause analysis by its methodology, by these different stage of analysis, will consume too much resource, too much time. For that, from the beginning, in the first stage of the analysis, we need to check the significance of the failure. If it's not significant, don't proceed with the RC. Usually, some criteria is used to determine if the RCA is required or not. According to the IEC standards, any single event with large effect, catastrophic effect, sporadic effect, or a multiple similar undesirable event, it's not catastrophic, but it's repeated several times. So we have now the risk from the reoccurrence, or a parameter moving out of a defined tolerance level, or a failure that involves critical item or critical equipment or activities. All these criteria let the failure be significant, be risky. So it's justified to investigate with the RCA. The bridge standard as well puts some parameter and make like a matrix with the frequency and the impact of the failure. Frequency of the failure and the impact of the failure. For very low area, it's not required, the RCA. For the second area, it's optional according to the available resource or not. The third area, area number 3, it's recommended to the RCA. Area number 4, mandatory to be done. Area number 5, customer request shall always take precedence. Shall be done. So, applying a structured root cause analysis depend on the impact and the frequency of the problem. Depend on the risk of the problem, the risk of the failure. As it's resource consuming, it's not practical and it's actually not logic to be done for every failure. This is impossible in reality. So we have some criteria to do root cause analysis or not. If not, we can go to the troubleshooting. If the problem is very minor, we can use the instant matching. Now, another strategy arose actually some years before called defect elimination. What is it? Defect is defined as anything that erodes value. According to the definition, asset is anything that give value to the organization. So the defect is anything that erodes this value. Any deviation from the perfection is a defect. Defect can lay hidden from view and may not become apparent until it causes a failure. With the defect elimination process, we need to catch these defects in order to eliminate them from making failures. Defects aren't just physical problem or equipment failure. They are the small niggly problems that cause repetitive breakdowns, that may lead to safety hazards, that can make hurt morale. Defect elimination now, it's about getting right from many small problems in your plant so they never show up again. If we don't seek them out proactively, then we can expect to come across them reactively after they make failures. So defect elimination is all about fixing forever than forever fixing. It's about get the bugs out, the small things, the very small things, eliminate them. It's a bottom-up approach coming from the down, from the operational level to eliminate the small repetitive reactive work before it happens. And in such a way that it will not happen again. A defect elimination program then is a structured process, should be a structured process system in our organization. Adapt to become more consistent and reliable in eliminating the defects. It's applicable to anything, core themes of our organization. And it's a continuous process, never ending process. We need to have a system to let the operation level, the technicians, the operators, anyone in the operational level in the organization, in the lower level in the organization, to identify the defects they have, to identify the defects they see, to identify the defects they feel, then to have a process to prioritize these defects, analyze them, develop solution, implement the solution, verify the improvements. Very simply, if the root cause analysis look for the very significant bad actors, defect elimination is looking for the many trivials. It's the Pareto analysis, the 80-20 rules. Root cause analysis look for the significant few that lead to significant failure. They are few in their number, but significant in their effect. So we use the root cause analysis for these few in their number, but significant in their effect, what we call them the bad actor. What about the huge amount of others failures? They are minor. Every one of these other causes are minor in its effect. But if you collect all of them together, their effect will be huge. These minors can't be, it's impossible, it's unpractical to be investigated with the root cause analysis. But the workers, the operator, the technician, they they deal with the problem, they deal with the equipment in daily basis. They know. They know the causes, the roots of this minor failure. So we need to collect all these causes from our workers, from our frontline staff, investigate it, and put corrective action as well. So the root cause analysis is a bottom-up approach for the bad actors based on the significant criteria. But the defect elimination is a bottom-up approach. Look for the base, for the huge, many trivials causes. Defect elimination program unleash the creativity of our workforce by proactively engaging them to identify flawed systems that influence our organization. So when it comes to defect elimination, remember to sweep the small stuff. That's the goal. To engage all employees in the defect elimination process, to eliminate the imperfections in our processes, in our equipment, provide our employee the ownership in the improvement process, and ultimately the success of the business. This system encourage frontline employee to find and remove defects at the source. An active defect elimination process will efficiently and effectively and economically as well minimize the need to conduct root cause analysis. According to the studies by the inventor of the defect elimination, the 1% rule, if you investigate 1 out of 100 work order, corrective maintenance work orders, into a defect elimination process, you will reduce the number of work orders by 37.5% over 3 years and 70% over 8 years. Reduction in the failures work orders by investigating 1 out of 100 work orders. So don't just fix it, improve it. And by the way, this is the title of one of the main reference about the defect elimination. One very important, very nice handbook. Don't just fix it, improve it. Linus Lided and Mark Pitch. Linus Lided, the first one actually invent this defect elimination system while he's working in DuPont. Make an investigation looking for the key enabling process for the maintenance to prevent failures, and looking for the potential improvement in the equipment uptime. The availability of our equipment, typically the availability is about 80 to 85%. When we make a good planning for our maintenance, preparation in advance for all the elements required to do the tasks, this will eliminate the downtime. So it will have a good impact about the availability, about the plant uptime. It will increase the plant uptime about 0.5%. If we do as well scheduling, not only planning, scheduling as well. Planning is the preparation in advance for all the elements to execute a task. Scheduling is putting the right resource and the right time to executing the task. So planning reduce delays during executing the job, while scheduling reduce delay in between the jobs. So planning and scheduling will increase the plant uptime 0.8%. If you have a maintenance program, preventive and predictive, without planning and scheduling, so you have tasks, but no planning, no preparation, no scheduling, this will reduce the plant uptime. If we combine the maintenance program with the planning and scheduling, all of them together, it will have an impact of increasing the plant uptime 5.1%. If you add defect elimination to these 3 different strategies, plant uptime will be increased more, about 20%, which is great, actually great. Now we discussed instant matching, troubleshooting, root cause analysis, defect elimination. Which approach to utilize? Each one has its advantage. Each approach has its positives and negatives. Which approach to utilize? What we need is to put a failure management strategy. There is no one best strategy that will fit for all the failures. No one strategy will fit for all failures. We need to have a failure management strategy. What's failure management strategy? A proactive strategy to manage the failure and their effects to an acceptable risk. It consists of proactive maintenance tasks and or one-time changes, modifications, upgrading. A failure management strategy is a risk-based approach to look for the risk of the failure. The risk usually is a matrix between the likelihood, the reoccurrence of the failure, and the consequence of the failure. Maybe 4 by 4, 4 by 5, 5 by 5, 5 by 6, whatever you put it according to your organization. But we need to have a risk matrix for our failures. In our failure management strategy, we need to put this matrix to look for the failure. If it's high risky, so it's considered one of the bad actors that considered from the significant few. So root cause analysis is justified. If it's not very high in this red zone, so it's not justified to put your resource on this moderate risky failure. Troubleshooting is enough. If the risk is low, so this area include the trivial menace. Defect elimination can work here. Don't keep any area without the suitable failure investigation system. For the high risky root cause analysis, the team-based approach, the methodology of the investigation and analysis with the analytical tools. For the moderate, go to the troubleshooting to get the immediate cause, to know the failed component, repair it. For the very low risk, don't keep them. Defect elimination will work well in this area. So the failure management strategy is a risk-based approach to look for the risk of every failure in order to determine the suitable investigation technique for this failure. As well, according to the risk, we will determine not only the technique, but also the level of the investigation, the personnel involved in the failure analysis, the resources that will be put in the investigation should be according to the risk of the failure as well. And the corrective action within the RCA, we do a cost benefit analysis in order to check the corrective action, is it suitable or not. So the properly validated root causes should be non-negotiable, but the solution, on the other hand, are negotiable. The solution, the corrective action, also will be based on the severity, and the likelihood will be based on the risk. The hierarchy of the controls indicate that the higher the solution sit in the hierarchy of control, the more effective they will be in the long term. But sometimes it will not be as a cost-wise effective. So as a conclusion, failure investigation and analysis techniques are very valuable tools, very valuable tools that complement each other and don't contradict each other or replace each other's. We need instant matching. We need troubleshooting. We need root cause analysis. We need defect elimination. All are needed. The proper balance of these tools can add extreme value to any holistic reliability engineering system, as well as engage the creativity of the workforce in solving the company's problem. The high reliability organization has a holistic view, a failure management strategy within a maintenance management strategy, within an asset management strategy, within the strategic business management strategy. Finally, a paradigm need to defeat. We never seem to have the time and budget to do things right, but we always seem to have the time and budget to do them again and again. So we need to stop for some times, put a system, let everyone in our organization be familiar with the system, then put a responsibility matrix and get those responsible about every technique well trained, have all the competences required to do the job. Then start your system and improve it day by day. This is the idea of the risk management, risk-based failure management strategy. Hope that you get the idea and you will find it, inshallah, useful in your organization. If there is any questions, I'll be happy to answer.
All right, great. Thank you, Alaa, for that great presentation. So as he mentioned, we're going to go ahead and open it up for questions at this time. So if anybody has a question for Alaa and they haven't already submitted it, go ahead and use this time. Just find the question panel on your webinar screen and hit submit. And we'd be happy to take a moment here to answer your questions. I know we're a bit over our time, but we will just pause for a moment to allow everybody to submit their questions if they have any. But otherwise, Alaa, another question that did come in during your presentation, this person is simply asking if they're looking to speak with you more and connect with you additionally, how can they go about getting in touch with you?
It will be my pleasure. Actually, anyone need to contact me. Here is my email and my WhatsApp phone number, my LinkedIn account. Please feel free to contact me anytime. If you need any support about the any of this system, I'll be very happy to support you and your organization. Please feel free to contact me using the email, the WhatsApp, the LinkedIn, all are available.
Okay, great. Now it looks like we've got another question here. So this person is saying that they first of all said, thank you, very interesting presentation. And then following that, they shared regarding the RCA process, the fact collection and the analysis feed each other. Are there rules to organize the information to avoid an endless process?
Sorry, again, the question about the root cause analysis? What?
Yes. So about the root cause analysis, are there rules to organize the information gathered to avoid it becoming endless?
Yes, sure. A lot of different analytical techniques are available, like the fault tree analysis, the cause mapping, cause and effect analysis. There are several tools in order to collect the data, to put them in the right order, organize them in order to can reach the root cause of the problem. A lot of different tools are available. There is no one best tool for the as analytical tool for the RCA. Each tool has its characteristics. We can't say advantage and disadvantage. It's characteristic. 5 whys is a very simple tool, but it's very linear. It's linear. If one effect has multiple causes, now we have branching. 5 why will be complicated. Cause mapping in this scenario will be good. If you have a lot of branching and a multiple of and or, the fault tree analysis in this case will be more suitable. If you need to make a great brainstorming, there is no clear idea, and we need to make a brainstorming to put all the possible causes that lead to one particular failure, fishbone or the cause and effect analysis will be now the most suitable tools. So actually, in some cases, we can use several tools together. It's according to the case itself. There is no one best tool. All are working depending on the actual case that we investigate.
Okay, great. Thank you, Alaa. All right. It looks like that does it for our time for today. Alaa, was there anything else that you would like to add before we start wrapping things up?
Thank you so much. Thank you for all the attendees. Thank you for as well for those who will watch the recording of this webinar. Thanks for Mobius Connect team for hosting and organizing this wonderful week of webinars. It's my pleasure to participate and hope that the attendees get a value from this webinar.
Yes. And Alaa, thank you so much for your time, for your patience. I'm so happy that the connection held up. It was a great presentation, and I know you put a lot of time and effort into it. So thank you so much for being a part of WOW 11. We really appreciate it. And thank you to our audience as well for your patience and for tuning in with us today. So that being said, to begin wrapping up here, just a so as a thank you for attending WOW 11, if you haven't joined one of our previous sessions, I just want to make you aware that we're providing a 50% off discount on your conference pass to the CBM and Reliability Connect live training conferences happening later. So one in a few weeks in Mexico, and then another happening later this year in Perth, Australia. So feel free to use code WOW50 with any of our upcoming conferences to reserve your seat. The events include certification training opportunities, hands-on workshops, case study sessions, and you guys can all visit MobiusConnectConference.com to learn more about the live sessions and live events, or we'll include a link also for you to register in the follow-up email after this webinar is completed. And then also we have one more session as a part of WOW 11 today. So hopefully you guys will be able to join us for that one too. It's Leveraging Condition Monitoring Technologies for Business Decisions, presented by Chris Coulson of Allied Reliability. So we're headed over there shortly. So hopefully we'll see you guys there. If not, hopefully we'll find you at another WOW 11 session this week. Again, we really always appreciate your time and attention and participation. So hopefully we'll see you there. And then lastly, just as a quick reminder, look out for an email from us containing the on-demand library access for all of the WOW 11 sessions, including Alaa's session that you just watched here today. You'll find every WOW 11 session there. And then also attached to that email, you'll find your certificate of attendance. Feel free to share those up on social media. We always love to see and engage with those and to support you along in your continuing education journey. So feel free to share those, tag Alaa, tag us, tag Mobius Connect, and that way we can see it and support you. And then if you're interested in engaging with other industry professionals, or if you'd like to participate on the industry's live feed and forums, you can visit MobiusConnect.com or create your free profile. And also just be sure to follow us on all major social media networks at Mobius Connect if you don't already. You can stay up to all the date with the latest community happenings there. And then if you guys have any questions whatsoever, feel free to contact myself, our Mobius Connect team at info@mobiusconnect.com. If you need any support with WOW 11, if you have any suggestions for future sessions, if you just need any help at all, feel free to reach out to us. We're happy to help. But thanks again, everyone, for joining us today. Again, thank you for your patience. We really appreciate you, and I hope to see you at another WOW 11 session soon. Thank you, guys. Have a good one.
Thank you, everyone. Thank you so much.